So we're gonna talk about contact of bodies today. So in a lot of applications, you have two bodies of materials that can come together and contact each other. And in those cases, you actually get stresses that get produced by that contact between these two bodies. I'm gonna first cover spheres to kind of get started here. Again, there's the summary of elasticity equations. There are three governing equations. Um, and then we have six strain deflection relationships. We have six strain relationships. That's 15 equations and 15 unknowns. And typically you will use finite elements to solve problems like that. But it turns out that there's a lot of applications where doing finite elements may not be the best approach, given the fidelity that you need in these models to really get an answer. And for a lot of problems, you can actually get an answer with closed form solutions, which is what this course primary objective is. I do teach a course in the spring or at this university that looks at applying finite elements to solve some of the problems that you see in this course. But again, the focus of this particular course is to look at closed form solutions that are handy, that can be used in actual applications. So, and so we'll get started again. External loads are provided to a system. In this case, when two bodies of materials are coming into contact, the external load is caused by these bodies of materials coming into contact. That produces an internal load within each of those bodies of material. And we're looking at, when these bodies of materials will fail when these two bodies of materials come in contact. In this case, you'll get stresses internal to the structure for each of these bodies of material. And then you have strains and deflections that can be calculated because they're all connected with each other through this map that I have been covering that came from my book. So there are a lot of applications where you will encounter bodies of materials that are in contact. There are some assumptions that need to be made in this scenario that we'll be discussing today. First, we're going to assume that the bodies of material are isotropic. If you recall, an isotropic material is one where the properties do not vary according to orientation. So it's independent of orientation. The modulus and Poisson ratio is the same. The second assumption that is made is that the two bodies of material remain on their linear elastic properties or their elastic properties. We'll also assume in this theory that the contact area is small relative to the radii of the contacting bodies. And then we also assume that these contacting bodies are smooth. So there's no asperities because if you had asperities, what will happen then is you'll get a shear force, some amount of shear force, but you may also get localized additional stress concentrations near the contact location. So we're only going to look at normal forces in these calculations. And then we're going to assume that the strains are small, and then we stay within a linear elastic regime. And finally, we're going to assume that the bodies are going to come into contact in a frictionless way. We can expand this to more advanced theories. For that, I recommend that you look at a course that deals with contact mechanics. A course like that will go into a lot of details about many different situations you may encounter in real life where you may have friction, you may have shear forces, and many other situations where you have lubricants applied, and things like that. We'll also talk about the idea of Hertz contact, and that's a situation we'll be covering today. The theoretical contact area of two spheres, if you brought two spheres together, the theoretical contact point is actually a point. They'll come down to a point. The theoretical contact area of two parallel cylinders, so you take two pencils there, or two cylinders, and you brought them together into contact, what you will find is that you get a line. So as a result, the pressure between the two curved surfaces will be infinite. And that is not realistic. We know that if the if everything came to a point, it's unlikely, like in real life, you don't see, like if I were to bring two spheres together with very little load, obviously the two spheres are not breaking apart just by bringing it to small contact. So we know that infinite stress is not really a reality. In reality, a small contact area will develop, and it's being created through elastic deformation. Um, but if those spheres were rigid and they came in, that's going to give you a point at which they contact each other, those two spheres, and that will be an infinite stress cost, but that's not what happens in reality. In reality is that when the two spheres come into contact, they'll deform in such a manner that you form a small radii, a small circle where the contacting area is occurring. And that limits the stresses quite considerably. This type of approach, looking at the problem from that perspective, is called a Hertzian contact stress problem, or Hertz contact stress problem. Here, what I'm showing is, and showcasing to you, is different applications where you may see two contacting bodies coming together. In spacecraft applications, in many cases, use reaction wheel controls, RW, reaction wheel controls, RWC, that provide stability to a spacecraft, or you may have gyroscopic stability that's needed, and these bearings can provide that. The bearing sits inside this groove and is able to smoothly allow rotation or high RPMs, and that's allowed by something like that. But there'll be a lot of contact force occurring there between the ball and the raceway. We call it the raceway. There are also linear bearings in real applications, gear problems where you have two gears coming to contact. Those situations you will have also contacting bodies of material. The first scenario I want to study with you without deriving equations. So in this particular lecture, I'll be not deriving equations where this came from, but rather present equations for you to know what they are, and we'll then apply it to maybe one or two problems. But my main goal here is to really showcase to you what the equations are for predicting the stress distribution in a sphere when two bodies of material are coming into contact. The first scenario I'm presenting to you is two spheres coming into contact with a force F applied to each of them. Obviously, if I apply a force F to the top sphere, it's going to get reacted by a force F in the bottom material by equilibrium and Newton's law of motion. In the top material, I have sphere 1, which has modulus E1 and Poisson ratio nu1. The bottom material is made of Poisson ratio nu2, which modulus of Young modulus E2. These two materials are coming into contact, and due to the elastic deformation that occurs in this region, you're going to have some amount of elastic deformation in this region right here. You're going to create a surface that looks like a circle where the two materials are contacting. And that as more force is applied, the greater that contact area becomes. Imagine trying to do this in finite elements. I've done it myself, and I'll tell you, having a simulation that can quickly give you answers is useful. In this scenario, you'll develop a contact pressure as well. So there will be an average contact pressure across that area where things are in contact. And the first thing I want to point out is that the solution provided for Hertzian contact area is provided here. So you can see here, that's the contact area. In this case, you have the radius A provided of that contact area, that's circular. So that's the radius of that circle where things are into contact. And you can see here, it depends on the force F. It depends on the Poisson ratios of the two materials. And it also depends on the radius of each of these spheres. And so that's actually very useful here. You can actually look at many different scenarios now. You can look at what happens when one of the materials is extremely rigid, meaning you have basically a rigid surface. This goes to infinity E2, and now this simplifies to a new condition that you can quickly analyze. You can analyze a lot of different conditions in a similar manner. You can also calculate the contact pressure. In this case, that's the maximum contact pressure occurs at the center, and it's given by 3 times the force applied divided by 2 pi, and then the radius of that contact area, a squared. The radius is a in this small a in this case. The point I want to make here is that this information, both of these depend on force, you can see here, and here in this case, it depends on force, but the cubic root of force, while here it depends linearly on force, which is quite interesting. You can also calculate what is the amount of indentation you get, basically how much these two spheres move with respect to each other. That's the calculation here. The displacement on the center of the spheres is given by this formula. And again, it depends on, and this should have been capital R and capital R, but small r is fine. Here, what I intended to say is the radius of each of the spheres. But that's the formula that you will use to calculate the displacement of the center of the spheres. If you want to calculate the principal stresses, which are generated, the maximum stresses will be generated along the z-axis. And when I say z-axis, you can see here that x and y is a plane where the spheres lie, while z is the center of axis of revolution. So the z-axis is going right through here, and so y is going right through the contact area. So z is measured from there. And what you see here is along z is where you get the maximum stresses, and that are the principal stresses. And you can determine, you definitely want to make sure it doesn't pass, doesn't exceed the yield of the material. So you can actually do that calculation if you wanted to. But you essentially get the P max times all this is a formula for the principal stresses. This formula, you can see here, that depends on the depth Z, and it depends on the radius A. So that's what you see there. In addition to that, you see the Poisson ratio showing up. You don't see modulus showing up, which is quite interesting. You also get the sigma 3, which is the stress in the third direction, is going to be equal to this formula, which again does not depend on the Poisson ratio or the modulus, which is quite interesting. The principal shear stress, as we discussed in many lectures now, is the difference between the highest principal stress minus the smallest principal stress divided by 2. And the absolute value of that is what the maximum shear is. So I'm gonna pause it right there.